Hello everyone, welcome again to Modeling Methods in Mechanical Engineering, and today we're going to actually finish up the topic of curvilinear coordinate system. It's not that we're not going to see it again, because down the road we're going to attempt to solve differential equations in such curvilinear coordinate systems, and that's precisely the reason why we actually study these and look at the metric tensor and look at the way we actually perform integrations by defining the different differentials of chord length or areas or differentials of volume. And what we're going to do today is look at how we actually express these vector operators, the differential vector operators in curvilinear coordinates. Things like the gradient, the divergency, the curl, and the Laplace, which are the four main differential operators that we study for Cartesian coordinate system. We're going to do it also for curvilinear ones. Now, when it comes to these operators, I can tell you that we cannot, well, we can, but we are not going to do it for the general case of general curvilinear coordinate system, because the form for these operators gets to be too large, too complex, too convoluted, actually a nightmare in some cases. So what we're going to concentrate on is on the orthogonal curvilinear coordinate systems. Those are the ones for which we are going to define these vector operators, the differential operators. And even though we're going to confine our discussion to orthogonal systems, these forms actually get to be complicated at times. So again, this is modeling methods in ME. And we are going to talk about differential operators for curvilinear orthogonal coordinate systems. Now we may ask why are we concerned with knowing how to do the gradient, the divergency, the curl, and the Laplace and curvilinear coordinates? Well, because ultimately what we want is to be able to figure out, derive governing equations, differential equations essentially, that govern certain phenomena like heat transfer, fluid mechanics, solid mechanics, electromagnetics, and so on. And we want to express those equations also not only for Cartesian coordinates, but we want to express them in other coordinate systems, which might be advantages from some frame of reference. For example, if we're analyzing things in pipes, we want to do it in cylindrical coordinate systems. If we're analyzing things in space for phenomena that propagate spherically, we want to express things in spherical coordinate systems. And what's more important is that us as engineers, what we want to do is find out the way where we can actually minimize or simplify the most. So where we can obtain the simplest form of a differential equation. And if we take a differential equation and happen to express it in a particular curvilinear coordinate system where we can actually cancel out and eliminate a lot of the terms, well, so be it. That's the one that we're going to opt to actually solve eventually. All right, so let's start with the gradient. And remember, the grad of a scalar function phi, we can also write as del phi, or nabla phi. Remember, no dot in the middle. This is a vector operator, and I said no dot in the middle, and the dot showed up. So no dot in the middle. And we're going to say that because this is a vector operator, this is going to result in some function 1 in the first direction, plus some function 2 in the second direction, plus some function 3 in the third direction. And notice that when I say E1, E2, E3, I'm generalizing to the specific curvilinear coordinate system. And remember, we're going to confine these to orthogonal ones. Otherwise, this final form that I'm going to show you is going to be a bit crazy. All right, so remember that the differential position vector is dr dx1 times dx1 plus dr dx2 times dx2 plus dr dx3 times dx3. Okay, this is a simple chain rule. R, which is a position vector, depends on x1, x2, and x3, and we're simply differentiating it with respect to each one of these three. Now, for orthogonal systems, the differential position vector can be expressed as h1 times e1 dx1 plus h2 e2 dx2 plus h3 e3 dx3. You go back to the notes where we actually derive these differential position vector for curvilinear coordinates. You'll find that it works out to be a function of the scale factors h1, h2, and h3, which, remember, only exist for orthogonal systems. h1, h2, and h3 do not exist unless the system is orthogonal. It makes no sense to take the square root of the diagonal members of the metric tensor, because you also have the off diagonals. So these only exist in this case. So then, the differential of phi is the gradient of phi dotted into the R. So the differential of phi is equal to h1 f1 dx1 plus h2. So I'm taking the gradient of phi, which is defined up here, and multiplying it times the differential of the position vector, which is this one up here, h2 f2 dx2 plus h3 f3 dx3. Okay, and all I have to do is some comparison here, because by also chain ruling, the differential of the position vector is also d phi dx1 times dx1 plus d phi dx2 times dx2 plus d phi dx3 times dx3. Simple chain rule. So I can just compare this one to this one, see, and just by comparison I can see that f1 is this one divided by h1, f2 is this one divided by h2, and so on and so forth. So by inspection, f1 happens to be 1 over h1 times d phi dx1, f2 is equal to 1 over h2 d phi over dx2, and f3, which is the third component of the gradient, is equal to 1 over h3 d phi over dx3, right? So we can just pack this up back into here and say, well, given a scalar function phi, which is a function of a three-dimensional curvilinear coordinate system, x1, x2, x3. That could be r, theta, and z, or it can be r, phi, and theta, whatever, right? The grad of phi, which can be shorthand notation del phi, is equal to 1 over h1 d phi dx1 in the first direction plus 1 over h2 d phi dx2 in the second direction plus 1 over h3 d phi dx3 in the third direction. Okay, pretty straightforward, at least for the gradient. The gradient is straightforward. So if I am given a function phi in cylindrical coordinates r, theta, and z, all I need to calculate the gradient of that function is the scale factors h1, h2, and h3. Okay, we know that h1 is equal to 1, h2 is equal to r, and h3 is equal to 1, right, in cylindrical coordinates. And then I take the derivative of this function with respect to r times 1 over 1. That goes in the r direction, er. And then plus 1 over r d phi d theta. I will be taking the derivative of this function with respect to x2, which is theta, divided by r in the theta direction, and so on and so forth. So now I have the gradient of the function. All right. So let me write what I just said. in cylindrical coordinates, phi would be a function of r, theta, and z. We know that hr is equal to 1, h theta is equal to r, and hz is equal to 1. So the grad of phi, which is noted as del phi, is d phi dr in the r direction plus 1 over r d phi d theta in the theta direction plus 1 over 1 d phi dz in the z direction. That's it. The gradient turns out to be kind of simple. But again, we're only talking about orthogonal systems. I can do this in spherical coordinates. So if I am given a function, I'm going to call this function f now, instead of calling it phi, because we know that there's a coordinate called phi, which is the azimuthal, the equatorial angle, I'm sorry. It's called phi. So hr is 1, h phi is r sine theta, and h theta is equal to r. Right? So if I need to take the gradient of this function f, which is del f, okay, then the operation will imply, well, take the derivative of f with respect to r and the r direction. Then take the derivative, take 1 over r sine of theta, multiply that times the derivative of f with respect to phi in the phi direction, plus 1 over r df d theta in the theta direction. Okay, so that's how we calculate the gradient of a function in spherical coordinates. So we need to include all these scale factors there in the middle of the operation. All right, let's move along. Actually, let's change the page because we're going to talk about another operator. So that's the gradient. Happens to be the most straightforward one. So the divergency, remember, is the divergency of V, which could be expressed as del dot V is equal to the limit when some volume delta V goes to 0. We call it omega. In this case, we're going to call it delta volume. 1 over this volume, the integral times the integral of the contour. We're going to call this contour S now. V dot n ds. Okay, this is just the divergency by definition. Now we need to do this in another coordinate system. And let's say that V is some vector field that is V1 in the first direction, V2 in the second direction, and V3 in the third direction. All right. Now I'm just going to write it for you, how it's going to end up being. The divergency of V, which again can be written, and again now this shorthand notation for the divergency del dot V is just implying that that's the divergency of V, but it doesn't make sense anymore because the nabla operator is not going to be, it's not going to have an exact form that is going to end up giving you this and for the gradient and this for the divergency if you dot product into it. So the way it's going to end up being is just 1 over h1, h2, h3 times the derivative with respect to x1 of h2, h3 times v1 plus the derivative of with respect to x2 of h1, h3 times v2 plus the derivative with respect to x3 of h1, h2, v3. Slightly more involved than calculating the gradient. Why would that be? Because, well, some of these scale factors end up being part of the differentiation process, so you have to take them into consideration if they actually match up with the variable of differentiation. So let me give you a couple of examples here. So in the cylindrical coordinate systems. Let's say that I give you a vector field V that is VR in the R direction plus V theta in the theta direction plus VZ in the Z direction. So I didn't call it UVW like we usually do because that's how it's usually done for in the Cartesian coordinates. HR is equal to 1, H theta is equal to R, and HZ is equal to 1. Those are the three scale factors for cylindrical coordinates. So I'm going to plug these into this equation, and what I get is the divergency should guide. I'm going to be able to just fit here del dot V. Again, that is a shorthand notation for it, but it really doesn't mean that that's how you calculate the divergency. What we should end up with is something that's a scalar, because remember the divergency of a vector field, this dot is implying that this is a scalar product, and therefore you should end up with a scalar, no directions, not E1, E2, E3 anywhere. So this is 1 over H1, H2, H3, which is 1 over R, right? And I'm going to just multiply it through, right? H2 and H3 is R, so that's going to be d dr of RVR. And then this is going to be 1 over R of, well, H1 and H3 is simply 1. H1 and H3 is 1. So this is d V theta d theta. And then 1 over R times H1, H2, d dz of H1, H2, that's R, right? Then that R can come out of the differential because d dz, R is not a function of z, and that R cancels with these R for the third component. So that's just simply dvz dz. As simple as that. So if I need to calculate the divergency of a vector field in cylindrical coordinates, this is how we actually do it. In spherical coordinates, so let's say that I give you V, which is VR in the R direction, so that we have a radial component of the vector field, V phi and the phi direction plus V theta in the theta direction. And remember that the three scale factors are 1, R sine theta, and H theta is R. So the divergency, and this is going to be a little longer, so I'm going to squeeze it here, which is written as del dot V, is equal to, all right, so I'm going to go by this form. 1 H1, H2, H3 is 1 over R squared sine of theta, right? And then let's look at the first one. H2 and H3 is R squared sine of theta. But the sine of theta will come out of the differential because this is the differential with respect to R, the derivative with respect to R. So the theta is a constant, it comes out and it cancels out with the 1 in the denominator. So this is, the first term is going to be 1 R squared, 1 over R squared, ddr, R squared, VR. All right. So that's the first term. By the way, this is the first term in the scalar expression. There's no E1 associated to this. Again, this is divergency, which is a scalar operator. Then the denominator again is 1 over R squared sine square of theta, sine of theta. I have H1 and H3, which is just simply R. That R I can take out because it's the derivative with respect to phi, and it cancels one of the R's in the denominator. And so this will be 1 over the sine, R. One of the R's remains, sine of theta, dv phi d phi. R sine theta, dv phi d phi. And the last one, 1 over R squared sine of theta. This is the derivative with respect to theta of 1, and this one H2 is R sine of theta. The R can come out and cancel one of the R's in the denominator, but the sine of theta cannot come out because this is the real respect to theta, so I'm going to have to leave it inside the operation. So this will be 1 over R sine of theta, the derivative with respect to theta of sine of theta v theta. And that's it. That's all I have to do to calculate the divergency of a vector field in spherical coordinates. All right. So let's look at the Laplace. The Laplace operator. So remember the Laplace of a scalar field. So given phi of x1, x2, x3, the Laplace of a vector field, which is the divergency of the gradient of that vector field, it can be denoted as del dot del phi, or simply as del square phi, which is not the same as del dot phi, right? So it's not the gradient of the divergency, it's the divergency of the gradient. This operation is not commutative. So we need to take the divergency of the gradient. So if we have the gradient of a scalar function, which works out to be this, and then this is V1, this is V2, and this is V3, right? Then I take the divergency of that expression, and at the end I'm going to have a combination of this expression and this expression with second derivatives. So that is going to work out to be as follows. So the Laplace of phi is equal to 1 over h1, h2, h3 of the derivative with respect to x1 of h2, h3 over h1 d phi dx1 plus the derivative with respect to x2 of h1, h3, h2 d phi dx2 plus the derivative with respect to x3, h1, h2 over h3 d phi dx3. Oops, this was a bracket. Okay. And that's how it goes. So let's see. If I do this in cylindrical coordinates again, and again, phi is a function of r, theta, and z, and the three scale factors go like this. So this plays out to be actually quite simple, because the Laplace of phi is going to be 1 over r d dr r d phi dr plus 1 over r squared, the second derivative of phi with respect to theta squared, plus the second derivative of phi with respect to z squared. That's sort of simple. So if I, for example, have a differential equation like the equation of heat conduction in homogeneous media, which we already derived and explained, and that equation has the Laplace in it, because through conservation of energy we figure out that would be the differential equation that governs heat conduction. Then if we want to express that equation in cylindrical coordinates, cylindrical coordinates, this is the differential equation that we'll need to solve. Not the second derivative with respect to r squared. It has to have those scale factors embedded in. So now let's try to do this again for spherical coordinates. Again, given this function f, which is a function of r phi and theta, and knowing that the scale factors hr is equal to 1, h phi is equal to r sine theta, and h theta is equal to r. All right. Let's try to do this maybe in 2 steps so we don't make a mistake. Oops, sorry. So we're going to take this expression here, and I'm going to say the Laplace of phi is equal to 1 over r squared sine of theta, open brackets, dr of h2, h3, this is h2 and h3 divided by h1, that's r squared sine of theta, df dr, plus the derivative with respect to phi of h1, h3 divided by h2, so the r and the r go away, so that would be 1 over the sine of theta, right? So h2 is this one right here, df d phi, and the last term is plus the derivative with respect to theta, that would be h1, h2, which is this one, divided by h3. So we'll just have a sign in the denominator, in the numerator, and this will be the derivative of f with respect to theta. So I am going to multiply this out. I know I can take the sine of theta out of this expression because this is a derivative with respect to r. I cannot take the r out unless I do the derivative of a product, right? So that sine and the sine will go away. So we'll have 1 over r squared, the derivative with respect to r of r squared df dr. In the second expression, right? Notice I can actually take the sine of theta out of the expression and multiply it with this sign right here. So this will be 1 divided by r squared sine squared of theta times the second derivative of f with respect to phi squared. And in this expression, there's nothing I can do. I cannot take the sine of theta out of this expression, obviously, because this is the differentiation with respect to theta. So this will be plus 1 over r squared sine of theta, the derivative with respect to theta of the sine of theta df d theta. And this is the full expression for the Laplace of a function phi. Oh, that's not a function phi, it would be a function f, what am I saying? So it's a function f, the Laplace of a function f in the spherical coordinate system. All right. This is the problem with teaching this class online. I don't have anybody to actually tell me about my mistakes. But at least I caught that one. All right, so that's a Laplace. Remember, the Laplace operator is an operator that keeps, if you're taking the Laplace of a scalar, you end up with a scalar. There's no resulting directions in this expression, right? This is just additional terms in a scalar expression. All right, and the final one that I'm going to cover, obviously there are more expressions, differential expressions, but we're talking about the 4 main ones that are relevant to engineering problems. Now the curl. And I'm going to say, okay, recall that the curl of V is equal, so again, given V, V1 in the first direction, V2 in the second direction, and V3 in the third direction. The curl of V is such that we can write it as del cross V, which doesn't necessarily mean anything because now we don't have an expression for what del looks like in general curvilinear systems, or at least, or even in orthogonal curvilinear system. It's just the way that we denote that operation. Is the limit when this volume goes to 0, which we used to call omega, it's the same thing, times the integral over the bounding surface n cross v ds. All right. So if I give you this particular vector field in a specific curvilinear system that happens to be orthogonal, for which we have scale factors h1, h2, h3, then the curl of this vector field v is equal to, which we can write as del cross v, is equal to 1 over h1, h2, h3 times the determinant of this matrix here. So this will be d dx1, d dx2, and d dx3, and this will be h1 times v1, h2 times v2, and h3 times v3. All right. So that is a general form of these. And let's attempt it again to do it for consistency. We're going to do it in cylindrical coordinates, and we're going to do it in spherical coordinates. So if in cylindrical coordinates, in cylindrical coordinate systems, okay, so if I have an expression v, which is vr in the r direction, plus v theta in the theta direction, and vz in the z direction, and the three scale factors are 1, r, and 1, then the curl of v, denoted as del cross v, is 1 over r times er, r, e theta, ez, d dr, d theta, d dz, and this will be vr, r, v theta, and vz. So we have to take the determinant of that expression. In order to do so, remember, I am going to augment this, and I'm going to do it in this. So this is ddr, vr, and this will be r, e theta, d theta, r, v theta. So, and I'm going to multiply this over all the diagonals, and then I'm going to multiply the counter diagonals and see what I get. And remember, all of that has to multiply 1 over r. So I get the curl of v, which is del cross v, and I'm going to do this in 2 steps, 1 over r, and bracket, and let's do the r term. This will be another bracket, dvz, d theta, and the negative r direction, I got minus d dz, rv theta, and that goes in the r direction. And then plus, let's look at the theta direction. Theta direction goes like this. So it would be d v r dz, and then negative, in the negative theta direction, I get d vz dr, and that now multiplies r e theta. And then the last one, the z direction, in the positive z direction, I get d dr of r v theta minus d vr d theta. So this would be a different key right there. All right. So in the other, I'm going to take that 1 over r and multiply it through. So the curl of v is equal to, or can be written as, del cross v. This is the 1 over r. So this goes like this: 1 over r dvz d theta. And then this r can actually come out and cancel this one, minus dv theta dz. In the r direction, the second one, you can see that this r and this r cancel each other out. This is outside the derivative, so it just multiplies through this one and cancels out. So that would be dvr dz minus dvz dr. In the theta direction, plus this r cannot come out of here, so this one remains 1 over r d dr of r v theta, and this r remains outside, so this will be minus 1 over r dvr d theta. All of these in the z direction. Right? So that's the expression for the curl in cylindrical coordinate system. So let's say if we have a vector field, a two-dimensional vector field in the r and theta direction, right, in polar coordinates, the curl will, so all of these will be 0. There's no z, there's no vz, and obviously the curl will only be non-zero in the z direction, perfectly perpendicular to the given field, right? And it would be 1 over r ddr r v theta, tangential component, minus 1 over r dvr d theta, the tangential derivative of the radial component. And that's it. So I'm going to leave it up to you to go out and calculate this for the spherical coordinate system, which should be a pretty simple exercise. But as you can see, these expressions are not trivial, right? This expression that comes out of this equation for the curl is not necessarily a trivial expression. And it can get very, very complicated depending on the coordinate system itself. You'll see that if you do this for the spherical system, where h1 is equal to 1, h2 is equal to r sine theta, and h3 is equal to r, this takes on a much convoluted kind of form. And that's in keep in consideration that we're talking exclusively about orthogonal systems. We're not even talking about generic non-orthogonal systems. We're talking about those whose metric tensor is perfectly diagonal. We have zeros in the off-diagonals and perfectly diagonal, where all the axes E1, E2, and E3 are actually perpendicular to each other. So this is it for today, and this should complete the material for this portion of the topics, which is curvilinear systems. And also it should complete the material for the first portion of the semester, which includes field theory and curvilinear systems. So thank you for your attention, and I'll see you next class.